Hi. Today I'm going to tell you a story. This happened a couple years ago, but like it says, 4 years ago from the time of recording, there was a change in how the building and the DOE as a whole measures what's in the drinking water in the school. What they used to do was they used to come in and they used to run the water fountain for like 30 seconds or a minute or 5 minutes, I can't remember what. But all of a sudden we got this letter in January 2017 because the DOE changed how they make their measurements. And instead of saying let's run it for a while, they said no, let's take the first bit of water that comes out, because when a student comes to the building first thing in the morning, they're not walking up to the water fountain and running it for a few minutes. Let's see what comes out. The fact of the matter is, any water that you're drinking that's delivered through any sort of system, any water delivery system, pipes, some small amount of solute from anything the water contacts can be dissolved. Yet last lesson we saw, even insoluble means a little bit soluble. So when you have this water sitting in pipes, it'll pick up some minerals, some ions from the pipe. One of the ions it could pick up is lead. Yes, lead is bad. Lead causes brain damage. Lead tastes sweet, so it's really dangerous around children. When you use lead paints on toys, they'll eat it and be like, this is delicious. Don't eat lead. But I see why some people, if they don't know any better, might end up doing it. There's a whole story I could tell you about the fall of the Roman Empire. I'll save that for the end. What happened, though, is that we've discovered that lead is bad to put in the pipes, but it's really expensive and time-consuming to go replace every pipe. So what we've said, I think, as a community, and don't quote me on this because I do not work for the city, is that we will replace pipes as we can, when we can. Specifically, we're going to look for the pipes that are contaminating the water the most first. So what ends up happening is the FDA and various city organizations will come together and say what level of lead is safe, is not going to cause any detriment. And the fact of the matter is everything is poisonous in high enough amounts and nothing is poisonous in low enough amounts. You could eat small amounts of arsenic or cyanide and be fine. There are people who do it on YouTube. Don't do it, and you can go find them on your own. I'm not even linking it here. But that's safe to say, a certain amount of lead in the water is fine. Not like you're going to get sick. You will be completely fine. And that number, they said, was 15 parts per billion. And that's this unit here that we've never seen before. Now, the title of this presentation is parts per million, so we're going to talk about that first. But what ended up happening, to cap off the story, is that of the 178 samples that were collected back in January 2017, 13 of them showed elevated levels of lead. Some of them were way more elevated than others. So those water fountains were obviously turned off, like this one too, and they were replaced. I think the one that was here, where is it? This one, no, yes, this one. The one outside room 131, that one was shut off for about 2 or 3 years until they went and assessed all the pipes and tested it, and that's now fine. It now passes. But now, since they changed the testing procedure, it's going to be a little bit more stringent and obviously safer for you. But this does yield a question. What is ppb? How is it calculated? And honestly, I'm kind of concerned. How does it compare back to molarity? That's probably something we should talk about. So unlike the previous unit we talked about, molarity, this is the formula for parts per million. This specifically refers to mass and mass, grams and grams. The reason we use grams is twofold. The first is that this is usually a situation, unlike molarity, we're only talking about lead. We're comparing lead to lead. This is similar to table G, where we're looking at like just ammonium chloride, and we're comparing ammonium chloride to ammonium chloride. There's no need to convert to moles if you're not going to be comparing between two chemicals, because mass does the job. Another thing I should talk about is why per million. Right? Why do we bring that per million into there? But to establish that, I want to dig into this formula a little bit. There are other parts per that you have had exposure to. The most common is parts per 100. And I can show you how you end up doing that. If you were to take a quiz, if you wanted to calculate your score, you took a 20-question quiz and you got 18 of them right, and you wanted to know what that score is, this is how you would do it. You'd say score equals 18 over 20 times 100. It's the amount correct over the total amount times 100. And then, of course, you'd get your 90%. Now, If we were to rearrange this, what we would get is score out of 100 is 18 over 20. In this case, the 18 is representing your solute, and the 20 is representing the solution, the total. But the reason they call it percent is that it's translating to out of 100. The same thing happens with parts per million. If we do that rearrangement, what we get is the parts per million amount over a million. And then that rearrangement says like the number that we get, if we say something is 18.6 parts per million, I know that's not parts per million, we're going to get there. But if we say it's parts per million, that means if you had a million parts. In cooking, they say parts when you're just measuring things out. You say a cup and a cup. It's just a comparison between the two. Your score out of 100. If it was 100 questions, you would get 90 right. There were 20 questions, you got 18 right. So we're comparing to like what it would be versus this specific case. So that's over here saying what it would be compared to this specific case. So parts per million, you have to do that dividing by a million for the number to make sense. The formula is rearranged to target the parts per million only, but that's why you end up multiplying by a million. You're saying, what would it be if there were a million, I guess, grams in this case? This would stand to reason if you were doing a part per billion calculation. You would do the same exact thing, except you would multiply by a billion instead of a million, or, if we wanted to save everyone some writing, 10 to the 9th. A million is 10 to the 6th. There are also measurements, parts per trillion, and parts per 1,000. Obviously, we've talked about parts per 100 as well. And the whole reason we do this is that the numbers that you get out need to be something that makes sense to you. It might be the case that for a certain solution, you have 200,000 parts per million. Well, that doesn't make sense to me. I can't process that as easily. But if we do some conversions, you'll notice that the conversion between them is a factor of 10 to the 3rd. So we could do this conversion. If I were to turn these into parts per million amounts, what I would get for each of these would be 1,000 smaller. If we're only taking a million samples instead of a billion, you're going to get 1,000 times fewer samples of your target. That is to say, so looking at these numbers, I think the 1.59 parts per million kind of makes sense to me. Like, that's a number I can picture, 1.6. But 0.0186, that's a little bit harder for my brain to calculate. So we pick the unit that gives us numbers that our brains can handle. The other reason that we use parts per million, I'm going to clear this all out, actually. The big reason that we want to use parts per million, I'm going to rewrite a lot of this just to make sense of it. If we had 1 gram, if we had 1 part per million, and we had 1 gram of solute, how many grams of solution would we need? Well, I mean, you can see the calculation there. Pretty easy to do that cross-multiplying. That would be 1,000,000 grams. Let's do a little bit of math, right? This proportion would work no matter what we did. So let's divide everything by 1,000 really quick, right? If I divide the top by 1,000 and I divide the bottom by 1,000, I still have the same ratio. And then let's do a quick unit conversion. 0.001 grams. Like I said, I don't like those big numbers or small numbers. 0.001 grams would be 1 milligram, and 1,000 grams would be 1 kilogram. And this is the real power of parts per million. In like really brief terms, 1 part per million is approximately 1 milligram per kilogram. If you have a kilogram of your solution, you know there's a milligram of stuff in it. 1 part per billion would be a microgram per kilogram. And so you can get that rough, estimate really quickly, and that's also a big power of looking at parts per million, per billion, per thousand calculation. The last thing I should say is I'm kind of glossing something over here. It's kind of hard to do a calculation on the mass of the whole solution when you got that solute in there, right? The solute adds in. So sometimes in the problems, you're going to see 100 grams of water, or you'll see 100 grams of solution. And depending, as long as we're dealing with small values, parts per billion, parts per million, and they're not huge parts per billion or million, you can say that the solute is a negligible contributor to the total mass of solution. That is to say, yes, I'm sure in 1,000 grams of solution, it's technically 999.999 grams, but that's close enough to 1,000 to say, yes, that's the amount of solute that's there, but it's pretty much 1,000 grams of water. That's going to be super helpful down the road. Now, in some examples, you're going to see that it's not the case. These are not negligible quantities. 17 is not a non-zero component of 183. However, if we wanted to calculate the parts per million, we could. In this case, the total mass of solution would be 17 plus 183. That would give us 200 grams total. Now, if we were to convert this into parts per million, we would get approximately 85,000 parts per million. Again, this is not the most useful unit. 85,000 parts per million. My brain has a hard time picturing what that means. I think in this case, this would be an instance where something like molarity, or maybe like parts per thousand, like 85 parts per thousand, makes a little bit more sense to me. I can picture 1,000 and what 85 would look like. But usually, parts per million is used when we have low concentrations, really low amounts. You're going to see this in the second problem. You can, given the parts per million, calculate the amount of solute. By just plugging in an X for what's missing, you can go do your algebra. And when you do, what you get is 0.114 grams. Now, in a 400 gram sample, that's about 400 milliliters, like a 12-ounce can, like a 12-ounce sample, you're having 0.1 grams. That's, you know, a tenth of a paperclip. That's a really small amount, and that gives you 284 parts per million. For the number for parts per million to make sense, the concentration has to be really low. This is for dilute solutions, basically. If you have a higher concentration, the number for parts per million ceases to make sense. I know what you might be thinking. Is there a way to get from parts per million to molarity? And the short answer is absolutely yes, but the longer answer is I'm not going to worry about it. We're not going to focus on that today. I do want to wrap things up by telling the story about the fall of the Roman Empire, but also mentioning that we have been exposed to now 2 different units of concentration. Both of them are a ratio of either solute to solution or solute to solvent. And honestly, any comparison of any mixture's components would be a unit of concentration, and you can convert between them. So I do want to fill in a bit of these. Weight percent would be mass of part over mass of whole times 100. This is basically parts per 100. They're the same thing. But you can see this happens. We use mass. It's a unit that is used. Volume percent would be very similar. Again, because the percents there we're multiplying by 100, but it's instead of using masses, we're using volumes. This happens a lot with alcoholic drinks, beer and liquor. Mole fraction works exactly the same way, except instead it's a ratio between the moles of solute and the moles of solution. So you can get a weight percent. You can probably convert to mole fraction pretty easily, but yeah. The hard part is to say moles of total solution. You do have to consider the solute and the solvent differently. And then don't forget that we do have that unit from table G. That's a ratio of grams of solute per 100 grams of solvent. We could hypothetically, given enough information, convert between any of these. And if you do see any of these, this is your key indicator that you have a solution. Last thing before I go. Turns out that one of the earliest metals we worked with as a culture was pewter, because it had a really low melting point. It was easy to shape and melt and pour into molds. Pewter is largely tin. And on the periodic table, tin and lead are right on top of each other. And so chemically they're similar. When you dig tin ore out of the ground, there's going to be some lead in there as well. And we didn't know it. And what ended up happening is these pewter cups were all distributed, and they found out that sour and old wine started to taste better, tasted a little sweet. And they figured out what was doing it, and this is where it got really bad. They said, hold on a second, so why not just add it to all wine, because it tastes delicious. And lead ionic compounds, salts, helped to make wine taste sweet. Now, I know what you're thinking, right? Like, if you eat a bunch of lead salts, you get, like, it hurts your body, you get brain damage. Yeah. And that's what was happening in Rome. And obviously we don't have a lot of forensic evidence to back this up, but some anthropologists do think that part of the fall of the Roman Empire was because all the people in Rome were adding these lead salts to their drinks purposefully, and it was kind of causing them to go a little bit off the deep end. And then they started making some bad choices and things fell apart. Now, I know that's a horrific overgeneralization of the whole process, I know, but it's an example where, you know, chemistry could have helped them out if they, or I guess this case would probably be a little bit more biology and medicine too, but it's always good to be aware of what you're putting in your body. Thanks for watching.